Hi folks, and welcome back. Sorry for the little hiccup there. Get booted off every now and then. So now let's take a look at a problem. If 10x minus 38 is less than or equal to f of x, which is less than or equal to x squared plus 2x minus 22, then determine the limit as x approaches 4 of f of x. I'll tell you right now, L'Hopital's rule will not work in this case. So in this case, what do we have? Well, let's just use what we can. You take the limit as x approaches 4 of 10x minus 38 is less than or equal to the limit as x approaches 4 of f of x, which is less than or equal to the limit as x approaches 4 of x squared plus 2x minus 22. So if this happens for all the values, we should have this working for us as well. So now, plugging that in, what do we have? So this would make 40 minus 38 is less than or equal to that limit as x approaches 4 of f of x, and this would be less than or equal to 4 squared plus 8 minus 22. And so notice our left hand side is 2, our right hand side 16 plus 8 is 24 minus 22 is also 2. So we have the limit as x approaches 4 of f of x is between 2 and 2, so that means the limit as x approaches 4 of f of x must equal to, and the reason why is by the squeeze theorem. So we need to state what we're using, and we're in pretty good shape there. Okay, so we got that limit down. Make sure you know that squeeze theorem quite well. Working through another one, we see evaluate the limit as theta approaches 0, sine of 3 theta times sine of 5 theta all over theta squared. One method is you could use trig limits. I'm actually going to up the game a little bit though. Let's try and use a couple things here. So we're going to use the property of continuity. Well, we don't really need that part, but we can break it up into two different limits. Notice theta squared is theta times theta, so we'll break it up into two different thetas here. So we have this limit as theta approaches 0 of sine of 3 theta over theta, and then the limit as theta approaches 0 of sine of 5 theta over theta. So now we can plug this in, and we get 0 over 0 in both cases, so we'll use L-hop in each case. Okay, L'Hopital's rule for that L-hop there. So this is the limit as theta approaches 0. The derivative of sine of 3 theta, remember the chain rule, this is cosine of 3 theta times derivative of the inside. So derivative of 3 theta is just 3. Derivative of the theta down below is 1. And then this is times the limit as theta approaches 0 of sine of 5 theta, that's cosine of 5 theta. And then we'll have all over in this times 5. Using chain rule once again, and derivative of theta is still 1. So what does this make? Well, we can plug in. You get cosine of 0 times 3 all over 1 times cosine of 0 times 5 all over 1. So notice that makes 3 times cosine of 0 is 1, so that's just 3 times 5. That's multiplication there. So the answer is 15. Now that's not the only approach. You could have used trig limits and used the fact that, so you could have written this as sine of 3 theta over 3 theta, but then you need to multiply the numerator by 3, right? Because the 3 over 3 would cancel in that case. And then times sine of 5 theta over 5 theta, and that's times 5 over 1, because the 5 over 5s would cancel. So because you can't just toss in 3's and 5's wherever you want. So what happens is, though, now you have that this limit, that's a trig limit that we know, that limit is equal to 1 in both of those cases, so you're left with 3 times 5, which equals 15. So two different approaches get you the same result. That's what we're looking for. Alright. So now let's start looking at graphs, see how we can find our answers in terms of what's going on there. So notice we have this labeled, so we have -1 is right here, -2 is right there, -3, -4, and then -5. So I'll draw this line and we'll put it as a dashed line. So notice we actually have, in fact, the way this is drawn, that's an asymptote. So in terms of x, this is, remember, x less than -5. So that means we're going to go to the curve and kind of draw it as we get closer and closer. So where are we going? Well, notice we're going up and up and up forever and ever, and we're going up to positive infinity. Okay. The second scenario would be when x is greater than -5. So we get to x equals -5, which is that asymptote right there, and we're going to get closer and closer and closer, but we're approaching from the right hand side. So notice we're going down, down, down towards negative infinity. Okay. Limit as x approaches -3 now. So we go 1, 2, 3, and we're drawing our curve here. And we need to approach it from both the left and the right. It has to be approaching the same place, otherwise it does not exist. And notice it is approaching the same place from both the left and the right of that value, and they're both approaching positive infinity. Okay, so now the next part, limit as x approaches infinity. So this is where we go out in this way, in this direction, further and further and further in the x. So in terms of what's happening here, notice the y value. What is that getting closer to? Well, it's getting closer to, here's -1 and here is -2. So it's getting closer and closer to -2. Whereas the mean time on the y value as we approach negative infinity, so I'll draw this on over, we're doing some oscillation back here, but the oscillation is getting closer and closer to +2. And that's our value for that piece. Okay. Make sure you're aware of how to read graphs and get those limits out of them. That's an important concept. I can guarantee you're going to see it in some form or another. Okay. So now, I mentioned before, I said there's places where L'Hopital's rule does not work. It will not work on this one. So sorry to break the bad news to you. It will not work on this part. So how do we actually go about doing it? Well, let's do the limit as x approaches infinity, and then I'll just make the minor changes for negative infinity and show you how that works. So this is, when you plug in, you get x times x minus 9 plus 1. And so when you plug in positive infinity, notice you get positive infinity plus 1. That's going to be positive infinity, but then you subtract off. So that's infinity minus infinity. What the heck does that mean? Well, we don't know. Okay, so we got to try and fix this a little bit. And there's a way to fix it. And hopefully you can guess from that previous example, it's multiplied by the conjugate. So I'll put all that in parentheses, and the conjugate of this thing would be just making that a plus x. Okay, so now taking a look at this, there won't be any funny business after we kind of go through this next step here. So this becomes x squared minus 9x plus 1, because when we square a square root it gets rid of that. But it goes minus x squared. Okay, and all of this will be over the square root of x squared minus 9x plus 1. And then plus x. Okay, so now moving forward from there, we get the limit as x approaches infinity of your x squareds will cancel, and you're left with negative 9x plus 1 all over the square root of x squared minus 9x plus 1, and then plus x. So what do we do at this point? Well, notice the degree of the numerator is 1. The degree of the denominator might seem tricky, but the square root of x squared, that's 1, and then the x is 1 as well. So what we'll do is we'll divide by x in both spots. Or you can say factor out in x, however you want to do it. But when we multiply by 1 over x, here's where your limit as x approaches positive infinity and your limit as x approaches negative infinity will differ. And I'll show you how. So in the numerator, there will be no difference between the two, whether this is positive or negative infinity. So you get negative 9 plus 1 over x. Everything's hunky-dory there. In our second scenario, you'll get the square root of x squared minus 9x plus 1 times 1 over x, which we'll talk about in a second, then plus 1. Okay, that's important, because what's going to happen at this point, we're equal for both the limit as x approaches positive infinity and limit as x approaches negative infinity. The approach is exactly the same. But here's where the trick lies, and so I'll put it in red just so you can see the red herring here. So when we go square root of 1 over x squared, oh, okay. So notice we've taken, if it's a positive value, it remains positive. So no harm, no foul there. But if it's negative, it'll turn into a negative value. So that means in this case up here, here's the big difference. So limit as x, we have a negative turning to a positive, so we got to account for that. So you still have the negative 9 plus 1 over x. You still have the square root of x squared minus 9x plus 1. But when we took that square root and squared it, we turned the negative version to a positive. So the way to fix that is we'll go negative square root of 1 over x, and then that quantity squared. Okay, and then plus 1. So that's going to be the big difference. That's it. Okay, so we can return to our value down below, and we'll see how that works out. But in this case, we get limit as x approaches infinity. We have negative 9 plus 1 over x, all divided by. When we make that 1 over x squared, multiply it on through, notice we get the square root of, we'll get 1 minus 9 over x, and then that square root's continuing on down there, plus 1 over x squared. Okay? And then we finish with the plus 1. Now plugging in, as x goes to infinity, notice what do we get? We'll get negative 9 plus 0 over the square root of 1 minus 0 plus 0, and then plus 1. So that makes negative 9 halves. Okay, so our answer for the first part is negative 9 halves. How is that different than our second part? Well, in our second part, notice we wrote it over there, you'll have a negative symbol come out in front of that. So you get negative, limit as x approaches negative infinity. So we get negative 9 plus 1 over x. We'll have negative, and then it goes square root of 1 minus 9 over x plus 1 over x squared, and then plus 1. Okay, so notice this will make negative 9 up top, but then we're approaching 0, right? And then we also have to think, okay, as we're approaching 0, are we approaching 0 from a larger number perspective or a smaller number perspective? So we have that 9 over x, and then we have the, what do we have here? Hold on, so 1 second real quick. So to give us an idea which direction we're going to have this approaching, negative 1 minus 9x plus 1 over x squared. And so notice I can take a look as to where this thing's approaching. Well, this will be approaching 0. Now will it be approaching from a positive direction? Well, notice that's a negative number up top. So yeah, okay. So for example, if we took something like, say, negative 100, notice you get negative 900 or negative 900 plus 1, that's negative 899, and then divided by 100 squared, so it's going to be 1 plus some extra number. So notice this number is going to be a little bit larger than negative 1, so we're approaching this from the negative side, so we're approaching 0 from a negative version. Okay, keep that in mind, that's actually quite important here. So when we go negative divided by a negative, that makes it positive, so this thing's blowing up towards positive infinity for that answer. Wowzers, right? So totally different results depending upon positive and negative infinity. Okay, so now for our next one, a function is said to have a horizontal asymptote if either limit of infinity or negative infinity exists. So how do we approach these real quick? Seemed like we struggled, but now we have L'Hopital's rule, so we'll use L'Hopital's rule whenever possible. What does that give us? So in our first case, what do we have? So L'Hopital's rule, we'd get limit as x approaches infinity of negative 8 over just 2. So that's negative 4, and that would be our final answer right there. Okay, we could do the same thing for the next one. We're going to use L'Hopital's rule, and so we get limit as x approaches infinity, or negative infinity, of the 8 up top, and then notice we have a 3x squared plus 7 down below, so that's going to make 0 as x goes towards negative infinity. Our next problem, and notice I didn't even have to go through that. I can recognize what is the degrees. If the degrees are the same, you just look at the coefficients in front. It would be negative 8 over 2 in the first case, which is what we have. In this case, notice the degrees are the same, so I just look at the degrees out in front. So I get 1 over negative 9, and that would be our final answer. Or you could use L'Hopital's rule twice. So the limit as x approaches infinity using L'Hop once. I get 2x over negative 18x. Notice actually, negative 2x, and then we have minus 11. Sorry, forgot about the minus 11. So 2x minus 11. So now I still have to use L'Hopital's rule, or I could recognize that the degree, as I mentioned, that would tell us a lot of information. Limit as x approaches positive infinity, so this becomes 2 over negative 18, which is equal to negative 1/9, which is what we had. Okay, for our next one, we're approaching positive infinity. So once again, we can multiply by 1 over x up top and down below. You could probably get away with L'Hopital's rule here too, but it'll probably be more efficient to multiply by 1 over x. And so notice we get, in this case, when we multiply by 1 over x, well, let's write it, x squared plus 15x, then we get 7 minus 2x. If we go times 1 over x, notice that means we take the square root of 1 over x, that quantity squared. It's positive, so they'll match up, and it's just 1 over x down below. So that makes this the limit as x approaches infinity of the square root of x times x squared times 1 over x squared. That's going to be 1 plus 15x over x squared, so that's 15 over x. And then we get 7, whoops, sorry about the little mix up there, 7 minus 7 over x minus 2. And so now what does that make? That makes square root of 1 divided by 2, which equals 1/2. Okay, move into the negative side of things. Remember, we're going to have to multiply by the negative version, because the square root of 1 over x squared, when we took 1 over x, we're approaching negative infinity, but when we square it, it turns into positive infinity. We didn't want that to happen. So you go x squared plus 15x times the negative square root of 1 over x, the quantity squared, and 1 over x, because we're approaching negative infinity this time. And so that makes negative the square root of x squared over x squared is just 1, plus 15 over x again. All over 7 over x minus 2. And we need a limit as x approaches negative infinity out here. Okay, so that makes negative square root of 1 all over, oh, I wrote positive 1/2 before. That should have been negative 1/2, my apologies. So this is negative 1/2 in that first scenario. So we have all over negative 2, and so the negatives will cancel. This one is the positive version. Okay. So you saw us work through quite a bit right there. L'Hopital's rule does cut down on time drastically. So how far can we go with L'Hopital's rule? Well, we can do ones that have x to the n. It really doesn't matter. We can still do those. How do we actually go about doing that? Well, we have the limit as x approaches infinity. Notice we have infinity over infinity, so this means we can use L'Hopital's rule. Okay, so derivative of natural log of x is just 1 over x, and then the derivative of x to the n is n times x to the n minus 1. Now you might say, oh, but n, what do we know? Well, we know that n is greater than 0. Okay, so that's important. So because what happens is this thing equals, we have 1 over n, and we can pull out in front because that's just a constant. Limit as x approaches positive infinity. Now this should be x to the 1 minus and minus 1. Okay, so notice 1 minus and then another minus 1 there. What does that make? Well, this should equal 1 over n, limit as x approaches infinity, and so this should be x to the 2 minus n. Right? So the other way to look at this now, this is the limit as x approaches positive infinity of, oh, we still have a 1 over n. You could write this as x squared let me do it this way actually. I'll look at it slightly different. I made a mistake. This was x to the, it should be negative 1 minus n minus 1. So with that in mind, the negative 1's cancel, so what are we left with? We're left with x to the negative n. My apologies there. So you get 1 over n, and then this is just 1 over x to the n. And so if n is greater than 0, which means it's going to stay down below, notice this whole thing becomes 1 over n times 0, which equals 0. Okay, sorry for the confusion there on that one. Alright, so now we're getting into an L'Hopital rule where it's a little bit different than usual. In this one, we're going to need to use an e and a natural log. The reason why, the x is up in the exponent. When you plug it in, you get 1 to the infinity. That's an indeterminate form. So the way to fix that, we'll go e to the, and then we'll go limit as x approaches infinity of the natural log of 11x over 11x plus 6 raised to the 9x. Now, this allows us to look at it a slightly different way. We'll get e to the limit as x approaches infinity. If we can write this as 9x times the natural log of 11x over 11x plus 6. Now with this, you could try and set it up where you could take a derivative, but taking a derivative of 11x over 11x plus 6 would be kind of nasty. That's where we can use properties of natural logs. And we'll pull the 9 out in front because of continuity properties. So now we'll have x times, this will be natural log of 11x minus the natural log of 11x plus 6. Okay, so this means we get e to the 9 to the limit as x approaches infinity. Now, this won't work out perfectly for us just yet, but we can make it work a little bit easier. We can write, instead of x, because we need to have some indeterminate form of the form like 0 over 0 or infinity over infinity, in order to do that, well, actually that won't work right there.